So can you show me how to attend lab class?
Lab class is going to be just like this for the first few. Um, Dr. Gereb and I have set up some virtual labs so we can actually do online.
Oh,
So what we'll do is on the Canvas page, there's instructions for the first two labs, which will both be virtual and online. And so um, you get the instructions, go to those sites, and then what we'll do is it will start a virtual class also through Zoom. And what I'll do is I'll sort of take you through it, show you how it works, and then we'll spend some time doing some of the activities together. And then you'll just finish the experiment by yourself whenever you have the time, collect the data, and write the report. And later on, we're not quite sure when it's going to happen, but a number of you have told me that you've ordered the kit for doing chemistry experiments, and when those arrive, we'll evaluate them and pick out however many to do, and then we'll do those relatively the same way. We'll meet up online. We will talk about what the experiment is, how to do it, and then you can do most of it during the time online, and then the rest you can do by yourself whenever. Collect the data and write a report.
thank you.
Okay, good question. Good one to start out with. Yes, Timothy.
I asked a question in the chat box. I was wondering what the actual lab times were. Your syllabus says 12 to 2, but on the web schedule it says 6:30 to 10.
It depends on which section you're in. If you're in my section, which is, let's see what the number is, 51423. That's the K7 section. That meets at noon. And if you're in Dr. Gegreb's section, that's 54543. That meets at 6:30. So you should when you signed up for the class, you should have one of those two numbers, and that'll tell you which section you're in.
Okay, I just wanted to confirm because the syllabus didn't match up with my schedule. So.
Yeah.
Yeah. Yeah. Each of my syllabus is going to be a little bit different from his, because he has his times in it, and I have my times in it. But for the lectures, I figure for the first week we might sort of do this together, and I feel like I kind of like being able to chat back and forth with everybody. But what the college wants us to do is to have what's called asynchronous meetings, which means that you could go in the lecture and go to YouTube and like look at the lecture whenever you like. So I'm going to try and do a little bit of both, but I figure the first week it would be nice for us to get a lot of the questions out of the way and have a chance to talk with each other, ask each other questions. So the lectures will always be, well, always, whenever they are meeting, whenever they are synchronous, it'll be at this time, at 4:15 for both sections. Any other questions?
So for another lab class, do we have lab today?
I don't think so.
Because in my Canvas, there's only your class.
Yeah, I'm starting lab on Wednesday, and I think Dr. Gegreb is starting it on Wednesday as well. But if you're in his section, you'd have to go to his Canvas page and check with him. But I'm starting on Wednesday.
Sure. Yeah. Thank you.
Oh, and one other thing. A lot of people have asked me, what the hell is a recitation? Fair enough. That is a good question. Because when I started teaching here, I didn't know what one was either. And basically what it is a problem-solving sort of workshop class where we'll have a worksheet with what we're doing in the lecture part of the class. And then we'll have a bunch of problems, we'll work through them, and then you will submit your answers in hopefully either Word form or PDF form to Canvas and get graded on it. So I pointed out in my Canvas shell anyway that I don't care if you get the right answer or not. That's because that's a test, and these are not a test. What they are is I'm trying to figure out how, how your minds work. I mean, my mind's a little twisted, so I don't know how yours is going to work the same as mine. So what I want you to do is try the problems, get through as many as you can do, but at least attempt them. I don't care if you get them right. I just want to see that you're trying to work through them. I mean, hell, maybe you'll come up with a better idea of how to do them than I can. And so what we'll do that way is you'll figure out what sort of questions will be on tests. And I'll figure out, maybe I'm not teaching this particularly well. I need to focus on this part of the subject or that part of the subject, or maybe explain it a little better. So actually, by you guys making mistakes, I will learn more. So that's why I grade for completion with the recitations and not for wrong and right answers. Okay, so don't be freaked out by them. It's good practice actually, and it's a good way for us to meet and talk about what problems you may have. So I've scheduled 2 hours for the recitations, but we can go longer if necessary. And don't feel like if you're a whiz at these things, like, maybe for the first couple, because they're going to be fairly elementary chemistry questions. If you feel that, hey, I got this, don't feel that you need to spend the whole time. But it would be good to spend some time at least in the recitation, because you get to know me a bit better. You get to talk with your peers in the class and maybe share some ideas back and forth. That was the nice part about being able to do this in person, was that a lot of the students in the class found out that they were really good teachers, and they learned so much more by explaining something to somebody else. And so that worked out great. I don't know if we're going to be able to, that's one of those things we're probably not going to be able to capture particularly well in a virtual environment. But, hopefully we'll be getting back to the real world fairly soon. So anything else? Genevieve.
Hi. So I am on the wait list, and I just thought I'd ask, since you mentioned the wait list, is there anything I should know specifically? I don't have access to the course in Canvas yet, of course.
Oh, yeah. What I need to do is the chair of the department actually mentioned that today, that we can get students who are on the wait list access to the Canvas shell, and I need to figure out how to do that. So I will figure out how to do that tomorrow. As far as the wait list, there were only 2 spots available. There's room for 35, and I gave out 2 ad codes today. And so the thing is, a lot of times, I don't know what it's going to be like with this sort of virtual class. We're all learning how to do this on the fly. In the real world classes, I would normally have 5 to 10 students drop in the first week or 2, and then we would add give ad codes to the rest. But I don't know if that's going to happen. I'm going to keep reminding people that if for whatever reason this isn't going to work out for you, you would rather wait until there's like a flesh and blood professor on the other side. Just drop it and take it later, because I've been getting so many messages from potential students saying, look, I desperately need this class. I'm starting at Davis in the fall, and I need to have this. I get it, so I will keep reminding people. But so far, it's only been 2. And so we need people to drop before I can add any more, unfortunately.
Okay, great, thanks.
Yeah, no problem. So that's some other questions there. I didn't get the names. Go ahead and ask your question.
Hi, Professor.
Yes. Who's this?
I got two questions to ask, actually. So one's about recitation.
Greedy.
For recitation, is that considered to be something that we're doing in, say, our lecture class or during our lab times, or is that on our own time?
It's separate. Recitation class is at the same time as lab. So for me, it'll be at noon, and for Michael Kagreb, it will be at 6:30, I believe. And so it's related to the lecture in that it will be reviewing problems that we are going over in the lecture class. But it's not the same as either lecture or lab, because it's like basically, like I said before, it's a problem solving workshop. And so you'll have the worksheet. So the worksheet's in Canvas. You can download it and look at it. And whatever ones you have trouble doing or you don't understand, we'll go over them during the recitation period. But then a week after the recitation period, that is due. So you need to work through all the problems. And like I said before, you do not have to have the right answers. So you can go and work through them. They don't have to be right, and submit them in either Word or PDF, something that I can open on my end, and then they'll be graded.
All right. And then my second question is regarding, you mentioned something about a lab kit.
Yes. We entered a contract with, I can't remember the name of the company right now, but because so many schools were going to offline or online environment, because the campuses were closed, they had developed these experiments that you can do at home. Like, that's a great idea. But there was such a huge demand for them that we weren't able to get them before the term started. And so what would have been the perfect situation is that we would have got them a couple of weeks before, been able to run them ourselves, evaluate them, see which ones work well, which ones don't. But we haven't had that chance. And so we don't know when they're going to arrive. It may be like in a week or 2 or 3 weeks. We're not really sure. But when they do, we're going to look through them, see which ones are the most promising, and then we'll do those during lab classes. Right now, we've got virtual labs set up to do that we have run through before. Timothy. Oh, wait. No, you had a second question. Sorry.
Oh, that was a second question, but it's like, for us as students, what do we have to do to attain these lab kits, if there is anything?
They will be sent to the college, and then they will contact you, and you can come and pick them up in a safe environment.
Got
so, it. As long as you're staying 6 feet apart, not coughing on each other, I think that's what they're looking for.
Got it. Thank you.
Okay. Timothy, you had a question.
No, I was just asking if those lab kits are something that we got to buy or pick up.
You have to pick them up. I think the college is purchasing them because we want to keep the classes as low cost as possible. So the lab manual is free, the textbook is free, and I'm being paid very little. So yeah, so we want to keep the cost down. So I'm pretty sure that you don't have to buy them, but I will double check on that. But you will have to physically go and get them. Okay, anything else? That's a good questions.
Hi, so I'm Zane, and I had a question
I
about
can see. Fantastic.
how will the test work?
The way I did the online testing last time was that I put the test on Canvas, and then you basically would just look at it and do it. You'd have 24 hours to do it. You wouldn't have to print it. If you didn't have a printer, you wouldn't have to print it. but just basically, write all your answers down and then submit them as either Word or PDF file. So you'd have 24 hours to do it. Because I found, and what I found was that a lot of my students who are doing poorly because they stress out. I mean, everybody stresses out taking tests, right? Including me. So, and my son here says he does too. And so I found that people who were getting 50s and 60s during a 90-minute test were now getting 70s and 80s and some getting 90s. Even though I made the tests harder. I mean, I deliberately made them harder and longer because you had a lot more time to do them, and they were crushing them. So either they were cheating really well or they got smart at chemistry. I prefer to think they were getting smart at chemistry. So that's how I'm going to do it.
Thank you.
That sound good to you? You got a lovely backyard there. I wish I was outside. That's really nice.
I know the weather is great over here.
Where are you?
Oh well, I'm at San Francisco. But
Oh,
So-
no. I'm in Pacifica, which was isn't foggy today. So anyway, I'll give some time at the end for some more questions. Why don't we get started? And then if you have any questions, yeah, just if someone will watch the chat for me, if someone can be in charge of the chat, I don't know if someone wants to be the chat monster, that would be very helpful. And then if there's a question, because I can't keep track of the chat and look at the slides at the same time, but if someone wants to be the chat meister, if they see something that's on there, just let me know. And you can either shout it out or hit the virtual hand raise thing. Okay. All right. So what I'm going to try and do in this class, and I think some students have said I've been fairly successful at it, is try and show what lessons we're learning actually are relevant to everyday life. I myself am not a chemist. If you looked at my bio, I'm a biochemist. And so because my two favorite subjects in high school were chemistry and biology, and I couldn't decide which one I liked better. And then when I found out you could do both at the same time, I thought that was, that was super, super cool. So what I'm going to try and do is, all the things that we learn, I'm going to try and relate them to something that either you do every day or you see every day, or is an important issue that's going on. And so, digesting food, that's something that we're going to be learning about when we look at combustion reactions and Hess's law, and how you can break down a very simple chemical equation, like taking sugar, adding oxygen, and getting CO2 and H2O. That's a combustion reaction. So if you burned your sugar, that's the reaction that would take place. That's also the reaction that takes place inside your body, except in a lot more steps. But the same thing happens. And so I'm going to try and show you how that works. Is anyone from the East Bay? You've probably, when you drive through the East Bay, you see that town that has all the huge towers that are used for what's called cracking oil. So here, over here on the right side of the screen, over here, that's what we call. Anyone tell me what that particular process is called? When you put crude oil in the bottom and then you fractionate all the different petroleum products. Anyone know what that's called? What's it called? Anyone?
Cracking?
Cracking? Yes, that's the industry term for it. It's cracking. That is correct. What's the chemical name for it? Couldn't hear that one. What was it? It's also the same process if you drink really, really good scotch. And that number of you are not allowed yet, so I don't want you answering that question. My son Roger here. Anyway, it's called distillation, if that sounds familiar. Distillation, and that is a physical separation where you take something, you take a mixture with a lot of different elements and products in it, and you separate them by their boiling point. And we'll be talking about why that works too. As you can see that each of these things, as they boil at different temperatures, you see things like methane boils at the top because it boils at a very low temperature. And stuff like asphalt that they use to pave roads with boils at an incredibly high temperature. So that's at the bottom. And so you can take like a really complex mixture of things and separate them in terms of their boiling point. And we'll get into how that works. Okay. So we're going to learn and discover different examples of changes in the composition and structure of matter. We're going to learn the different kinds of matter, different states of matter. Anyone tell me what the states of matter are? There's three basic ones, and then one that hardly anyone knows about. What are the three basic states of matter?
Gas, liquid, solid.
There you go. Excellent. What's the fourth?
Plasma.
Plasma.
Someone's looked at the slides. Excellent. Yeah, plasma. And so we're going to talk about each one of those, how to classify the changes that undergo one to another, and figuring out the energy involved. We're going to talk a lot about energy. You're going to get very tired of hearing the word energy. But energy and chemistry are so closely related that you really have trouble talking about one or the other. And so we'll learn that the difference in energy between those different states is related to how they change from one to another. And yeah, just like I said at the bottom, the changes in energy accompany those changes in matter. We're going to spend some time working on that as well. So it's just chemistry, when you get right down to it, it's just a study of the different composition, properties, and interactions of matter. And so if we go way back, the Greeks thought there were four basic elements, right? And everyone knows what the elements are: earth, air, fire, and water. And that was true for thousands of years. Really, the big increase in chemical knowledge is really only coming about the last 200 years or so, 300 years. And so, anyone who's watched, like, Lord of the Rings and all that kind of stuff, I've noticed that, one thing chemists, they called themselves chemists, tried to do was to take metals like lead and turn them into gold and silver. And of course, they couldn't do it. The funny thing now is we can actually do that. But you need like a nuclear reactor or a collider to do it. And it would cost you billions and billions of dollars to make like 1 gram of gold. So we're not actually, you could do it, but there's not really a whole lot of point in doing that. So I mentioned before, I'm a biochemist. I don't know what you guys want to do. There's a whole bunch of things you can do with a chemistry degree if you want to go that way, because it's connected to pretty much everything else. I know a lot of people who went into environmental science. If you want to go to UC Riverside, has a really good program in environmental science. I spent some time there. This is what I sort of was doing in my old lifetime. If you're interested in nuclear chemistry, of course, there's a lot of, one of the greatest nuclear labs, Lawrence Livermore, is right here in the Bay Area. And if you look at when we start looking at the periodic table, there's like 5 or 6 elements that are named after places right here in the Bay Area. And so it's sort of like it's a hotbed for that sort of thing. And so really, with knowledge of chemistry, like I said, you can go and do anything. So that's why I would suggest, you guys already know why you're taking chemistry, but yeah, there's a lot of different things you can do. Yeah, food science, biology, agriculture. A lot of you going to Davis, I've heard. That's excellent. I don't know if any of you are taking winemaking, but I would recommend that as well. And you need a chemistry background to do that also. So like I said, we're going to talk a lot about energy. Hopefully everyone's taken physics in high school? I hope. Yes, no? People have taken physics at some point?
Yeah.
Yes.
Yes.
Good. Remember any of it?
No.
So, okay. So basically, we really need to understand energy because we're going to be talking a lot about it. Because there is energy in chemical bonds. And we're going to be talking about, since we're talking about chemistry, we're going to be talking about bonding, atoms bonding together to form molecules, and that there's energy in those bonds. One thing that I was confused about, and I know that a lot of the students are confused about when they first start studying chemistry, is where do you think energy is released from bonds being made or bonds being broken? Which one releases energy into the environment, do you think?
Broken.
Broken.
Mm-hmm. Anybody else? I like how you jumped in. You were very sure. Anyone else agree, disagree? So quiet. I guess everyone would agree if you're being so quiet, right?
I think it's from broken, right?
Yeah, that's wrong.
That's wrong?
Yeah, it is. Energy is released when bonds are made, not when they're broken.
Oh,
Right?
okay.
When you think about it, it's like, that doesn't make any sense. I mean, there's energy there. When they break, that energy must be released. What you have to remember is it takes energy to break bonds. Bonds just don't break by themselves. You need to add energy to them in order to get them to break. So like when you're burning wood, for instance, you need to add a little bit of energy. You need to add a spark to get that fire going, right? It doesn't just happen by itself. And so that spark causes those molecules in the wood to break those bonds. And the energy as heat is actually released when you form bonds of water and CO2. That when you think about it, like that doesn't make any sense at first, but that's one of the things we'll go over, is that bond energy is the amount of energy you have to add to break them. And it's the amount of energy that's released when you make them. And so we call that potential. That's potential chemical energy. And so there's two kinds of energy if you've studied physics, and you're all expert physicists. So kinetic energy is movement, right? That's what kinetic means, movement. And so it's motion of atoms, particles, molecules. And that's basically where the energy from gas molecules comes from. It's all gas molecules are all flying around and moving. They're moving very quickly. And it's that kinetic energy that keeps them being gases, because there's so much energy in those molecules moving back and forth. When you take some of that energy away and the molecules start moving slower and slower, it becomes a liquid. You take more energy away, they start moving even slower than that, and they become solids. So the movement of electrons in a conductor, that's electrical energy. That's also kinetic because those electrons have to move. And we'll talk about conductors and semiconductors. I mean, hell, we're in Silicon Valley practically, right? Some of you may be interested in why silicon is important and what is a semiconductor anyway. That's one of the things we'll talk about. And so matter consists of atoms and molecules in motion. And it's just the amount of motion tells you what state it's in, whether it's solid, liquid, gas. So potential energy results from an object's position. Now, pretty easy to understand, gravitational position. If I have a rock over my head and I'm holding on to it, there's potential energy there, and if I let go, it's going to land on my head. So there's, gravitational energy, there's potential energy there. Energy stored in a spring. If I pull a spring apart, and it's going to snap back. There's energy stored in that extended spring. There's energy in food. When we break down, like the example I gave you before, when you eat sugar, there is energy in that sugar in the form of those chemical bonds that will be broken and then reformed into more stable bonds of water and CO2. That is energy stored in those chemical bonds. There's energy stored in charged particles, and this is something we're going to be talking about a lot. This comes up a lot, this electrostatic energy, where we have something that's positively charged and something that's negatively charged. As you may know, the closer you move those things together, the more energy you get, the more they want to come together, and the more energy it takes to pull them apart. And so it's a combination of how big those charges are and how close they are tells you how much electrostatic energy you have. Now that's going to come up a lot later on. And then of course there's nuclear energy, which is different from chemical energy. Chemical energy comes from bonds. Where does nuclear energy come from?
DNA or RNA?
Is that splitting atoms?
That's a biological nucleus. Now we're talking about a chemical nucleus.
Are you splitting compounds or like atoms?
They come from atoms, but where? Hint, it's in the title.
Proton?
Splitting the nucleus of an atom?
Splitting the nucleus, right. So we have particles in the nucleus, and who can tell me what particles are in the nucleus? There's two.
Protons and neutrons.
There you go. So it's those together in the nucleus, and when these nuclei fall apart, when they undergo fission, because they're radioactive, they undergo fission, they break apart into smaller nuclei, and that energy is released when they split. And so that's not chemical energy. That's something that people get confused with, because it comes from a chemical or something. It must be chemical energy, but it isn't. It's only from the nucleus. It is, because chemistry is basically, you might as well call it electronics, because chemistry is basically all about the electron. 95% of what we're going to learn about is based on the electron. It's shared electrons that make a chemical bond. It's the difference in charge between the nucleus and electrons that mean to give you whether or not an atom is charged, whether it's an ion. All this stuff comes down to electrons. And nuclear energy is one of the few things that has nothing to do with electrons whatsoever. And so if it doesn't have anything to do with electrons, it probably isn't chemistry. So let's look at some of the energy changes. Now, lower energy states are more stable. That kind of makes sense. You probably know that, nature doesn't really like high energy states, and that energy is removed from high energy states. They go to lower energy, and then they're more stable. For instance, if you're burning something, it gets converted into low energy states of water and CO2 and ash. In each one of those, there's not a whole lot of energy in any of those. They're lower energy states than was the original fuel you were burning. But one thing you have to know is that energy, you can't create energy or you can't destroy energy. It just goes from one state to another. And so it's conserved. We convert it from one form to another. Like we convert the potential energy of chemical bonds in sugar to heat and to the energy we use for, actively, moving around or storing fat for some of us. It's just changed from one kind of energy into another, and it's always conserved. And so when we're studying what's called thermochemistry, we'll realize that whatever energy we have at the start of a reaction, we're going to have at the end. It'll just be in a different form. And so we can actually use that information to make some really cool calculations and figure out how much energy atoms or molecules must have had at the beginning. We can figure that stuff out. So I just want to go back a little bit and talk about scientific methods. And so you guys are going to be doing experiments, and you're going to be doing something called formulating a hypothesis. And one thing that I keep wanting to mention to students, because they sort of run into this in their own lives, they run into it, you know, talking to other people, they talk to their family at Thanksgiving or whatever it is. And how many people have heard the sentence, oh, well, it's just a theory? Usually it's about evolution or something like that. They'll say, it's just a theory. Has anyone heard that before?
Yes.
Yeah.
Pretty much everybody, right? What people don't understand that a theory is the best thing you can possibly get. A theory is the very highest thing, like basically a science can attain, because what the theory is it means it's well substantiated, meaning that it's been tested over and over and over and over with all kinds of experiments, and they always prove that the theory is correct. It's comprehensive, meaning it explains a lot of different phenomena. And it's testable, and that is the most important thing. If you can't test something, then it ain't a theory. And so what people misunderstand is that a law isn't as good as a theory. And something that happened only about 5 or 6 years ago now was that the law of gravity became the theory of gravity. And that's happened, like I said, only 5 or 6 years ago. And so before then, we didn't understand how gravity worked. We had some hypothesis about it. We thought that gravity may work in some way, it may work in a different way, but it wasn't testable. So even Einstein and everybody else, they had an idea how gravity worked, but until you can test it, it's just a law. I mean, we know every measurement we've ever done of gravity always works. Any calculations we've ever done of, like, you know, we can send a satellite to Jupiter and bounce it off that and send it to Pluto or whatever using the laws of gravity, and it works. We didn't understand why. And it was only about, like I said, 5 or 6 years ago when gravitational waves were detected. When gravitational waves were detected, we finally had an explanation that we could test with how gravity worked. So now it's a theory. And so people will think, well, theory is not as good as a law. It's the other way around. The theory is the best you can have. And so if people have an objection to a theory and they have an idea of their own, particularly when talking about evolution, unless they have something that you can test with an experiment, it's not a theory. And if it's not a theory, we don't really have to think too much about it. So this is how it works. I mean, I won't spend a whole lot of time with this, but this is something I did for about 30 years of being curious about stuff and, you know, making observations and doing experiments. And then a lot of times those experiments didn't work. In fact, if any of you are thinking about being scientists, know this. Probably about 75 to 80% of the experiments you're going to do are not going to work. And so that's fine. If you can get a fifth or a quarter of your experiments to work, you're doing just great. And so when your experiments do work and they're consistent with the prediction you had, that contributes. You write a paper, you write it down, you send it in, and it gets published, and you get, like, famous. Well, you don't get famous. Then other scientists will read that paper and say, oh, this is interesting, and then they will do your experiment or variations of that experiment. And so if you keep testing and keep testing and keep testing, those observations become a law. That's great, but it's only when you have a hypothesis with a mechanism of how it works, and you can test that mechanism, then it becomes a theory. And then that's when you become famous. When you get a theory named after you, then, you know, then you're the woman or the man. So these are the different domains. When we talk about chemistry, here in this particular instance, we're talking about water. And there's a lot of different ways we can think about water. So there's the macroscopic version. I'm looking at water. I got gas, I got liquid water, I got solid. And in this picture, I see all three. I've got liquid here. That's my liquid. This is my solid. And the clouds, we know, are water vapor. So we got three different states of water all in the same picture. But then when we look at the molecular level, when they're gases, water molecules, that's what water looks like. We'll talk about the shape of water a lot because it's so important to biochemistry. I can't even tell you. I'll bore you to death with water. We'll talk a lot about water. So the water molecules really far apart when they're in the gas phase or when they're water vapor. They're very far apart. They don't interact with each other very much, if at all. When they're in liquid form, they come together and they actually form bonds that we call hydrogen bonds. And we're going to be talking about those a lot too. We talk about different ways that molecules can interact with each other. And we talk about their shapes. The shapes of molecules are extremely important, particularly in biological chemistry, but in physical chemistry and other kinds of chemistry as well. It's the shapes of those molecules that's really, really important. So they physically interact when they're in a liquid, but they're able to move around. They're still able to move, and so you have the liquid phase. When finally they freeze, you can see here at the bottom, when they're frozen, they're interacting, but they're no longer moving as much. Everything, but you have to remember, everything is still moving. There's still movement of the molecules. They're still vibrating. Anyone tell me when molecules stop moving entirely? When do molecules completely stop moving?
Is it when they're frozen?
It's like 0 Kelvin.
0 Kelvin, excellent. What else is that called, 0 Kelvin?
Absolute zero.
Absolute zero, excellent. Yes, absolute zero, you don't even detect, just not even vibration. So there's no movement at all. And so that is sort of the relationship between thermal energy and molecular movement. The more and more thermal energy there is, the more and more movement there is. And so once we get to the freezing point, they then become liquid. They sort of move further apart. They can still interact, but they move further apart so that they're free to move around. And then when they become a gas at the boiling point, they stop interacting entirely and take up a lot more space. So we've sort of gone through the three most common phases of matter here. So solid just has really the only definition of a solid, it has a shape. It has a definite shape. That's really pretty much all you can say about a solid. It's that it has a shape and it keeps that shape. So a liquid doesn't have a shape. It both flows, and whatever container it's in, it has that shape. So if I pour, water into a banana-shaped vessel, it's going to look like a banana. If I pour it into an apple shape, it's going to look like an apple. Whatever the shape of the container is. Now a gas is different in that it takes both the shape and the volume of its container. Funny thing about a gas container is that it's always full, which is like, huh? Yeah, it's always full. There's always gas in every part of it. So, but what about, you taking an empty propane container back to yes, you're taking a propane container back to get it filled with more gas, but it's still full. The difference is it's only atmospheric pressure when you take it back. When they fill it up, it's at much higher than atmospheric pressure. But when it's so-called empty, it's not empty. It's actually full, but it's only at 1 atmosphere of pressure. When it's at 1 atmosphere of pressure, it doesn't easily flow through anymore, and you can't barbecue anymore. So it has both a expander. So this has shape. This doesn't have a shape, And the gas, you can see, no matter what the pressure is, it's full. So it's just the more and more gas you put in it, the higher and higher the pressure goes, but it's still full, okay? And then when we study the gas laws, and that's something hopefully we'll get to at the end of the term. We'll learn a lot about how pressure, temperature, and volume are all related to each other. And then I said that, yeah, this is the fourth state. The only difference between gas and plasma is that in plasma, the particles are charged. So that's really the only difference. In a gas, basically, you have uncharged particles. You have molecules that aren't. In plasma, you have ions. What's the difference? Can anyone tell me what an ion is? What's the difference between a molecule and an ion?
Oh,
Go ahead. What's an ion?
Is it that an ion is charged?
It's charged. That's right. So why is it charged? What's the difference between an ion and a regular atom or a regular molecule?
It has like extra electrons
It either has extra electrons or
or
when it has
less.
extra electrons, what charge is it?
Negative.
It's negative.
yeah.
When is it positive?
When it loses an electron?
It loses an electron. That's right. So it has now, when it loses an electron, it now has more protons than electrons. Protons have a positive charge. Electrons have a negative charge. So a neutral atom has the same number. And so the number of positive charges, the number of negative charges are exactly the same. But when you lose an electron, now you have one more proton than electron, and you get a charge of +1. If you have an additional electron, you have one more, and it's negative. And then, so we're going to talk about ions quite a lot because it's quite important to a lot of chemistry. Now, one other thing you're going to be doing a lot is measuring mass. And mass is not the same thing as weight, which is a lot of, because if you ever feel like you're getting too fat, just go to the moon and your weight will be 1/6 and you will no longer have a problem. However, the bad news is your mass will be exactly the same. So the mass is a measure of the amount of stuff that's in some place, that's in a molecule, that's in, this pen, whatever. How much stuff is in there? Weight refers to the force that gravity exists on that mass. And so I'll ask you this way. If someone shoots a bullet at you in space, that bullet is weightless. Is it still going to harm you?
I think not.
Okay. Anybody else?
Yes, it will.
Okay, I've got a yes and I got a no. Anyone else want to get in?
I say no.
No? Okay. Okay, one more. Then I got 2 no's and a yes.
Yes, it will.
What do you think? So you've got predator chasing you in a weightless environment. You take a shot at it. Is that going to have any effect or not?
No.
No. Okay, so I got 3 no's and 1 yes. The answer is yes. So this is another thing that a common misnomer, because that bullet still has mass. It doesn't matter if it doesn't have any weight. It still has mass, and so that bullet on Earth has a certain weight. right? So like a bullet from like a 45 or whatever it is has a certain weight. In space, it has the same mass as it does here. And so you get shot with a 45 caliber in space, it's going to do the same amount of damage it's going to do on the Earth, because its mass is the same. Even if it's, you're weightless too. But if you went flying into somebody else, two astronauts bump into each other in space, they're going to hurt each other if they're moving fast enough, because their mass is still the same. So when we measure something, when we talk about doing chemistry, it's always mass, because it's the mass of molecules, it's the mass of atoms that's involved in everything. We never talk about the weight. So, because the weight can vary. The weight can vary on different parts of the Earth. There are places on Earth that have different amounts of gravity than other places. That may sound weird, but it's true. Not a lot different, but really, really small differences that you can measure, like 1 part in a million. And so, but the mass is constant. So we always talk about mass when we're doing chemistry. So why we talk about mass is because one of the key premises of chemistry is that matter is conserved. Just like energy is conserved, matter is conserved also. And so when we do a reaction, for instance, let's say we take hydrogen gas and we mix it with oxygen gas and we make water. Just know that it's not a balanced reaction. The mass, so if we want to balance it, we'll balance it. So the mass of the hydrogen and the mass of the oxygen, if this goes to completion, it all gets converted to water, the mass of the water will be exactly the same. Exactly. All the matter will be conserved. And so there's no detectable change in the total quantity of matter when you convert it from one type to another. If I convert all of my, let's say this is a liquid, I convert all of that to a gas, all of it is the same. That mass of gas will be exactly the same as the mass of the liquid. And that's really important, because if that wasn't true, it would be very difficult for us to do a lot of calculations. So we need this to be true in order for us to do any kind of calculations about reactions. And as it turns out, it is true. Now, how I can show you that is if I take, well, I love how this is called pre-beer. Like, it's called water and sugar and malt and yeast and whatever else. So if I put that, if I'm like making beer, I would never make beer in a bottle. I would make it somewhere else. But you can do it this way. So you put all the ingredients for making beer, you put the cap on it, it becomes beer. And so I get ethanol, I get CO2 from the carbonation, I get CO2, but the mass of that bottle is exactly the same before and after. There's no different. Even though a lot of this sugar is completely converted to ethanol and CO2, the mass is exactly the same. The same is true in your car. Most of you will have a car that has this kind of battery in it. It's just called a lead acid battery. And these have been used for years because you get a lot of energy out of it. You can use them to crank a motor to get it started. And so the lead gets broken down to lead oxide with the acid. And so it goes back and forth. You add electricity to it, you turn it back to lead. You take electricity out, it gets converted to lead oxide. But the mass of this battery, even if it runs all the way down and it's not producing electricity anymore, the mass of that battery is exactly the same. It's just that you've converted all the lead to lead oxide. And so it no longer will crank. All you need to do is just charge it up. And when you charge it up, you're adding electricity to it and you're making this reaction run backwards. And so when you have the reaction running backward, now it's to be able to produce electricity, and that reaction produces electrons, and that's what makes it run. But the mass is the same. for an adapter. So go up another 20 minutes or so here. Then we'll just take a few more questions. So one of the most important things to remember, the difference between elements and more complex compounds. So an element is a pure substance that cannot be broken down into anything simpler. Basically what it is, it's just an element, it's just atoms, that's it. There are only one type of atom in there. So what I mean, you can't break it down into anything else. Like water, I can break down. If I run electricity through water, I can convert it back into hydrogen.
Nanalo ko, tatapig kong gagawin eh. Bahala kayo.
Oh no, is someone ordering dinner?
Masat ko matagams. Matampak sa ganun.
All right. Okay. So if I can convert a complex compound into its substituent elements. I can't do that with a pure element. Like mercury, this beaker full of mercury, I can't break that down anymore. It's the only thing that's in it is Hg, mercury. There's nothing else there. So the known elements, we'll get to the periodic table, by their atomic number, which is also known as Z or Z if you're an American, and by the periodic properties. And we'll talk a lot about what periodic properties there are. I mean, why the hell is it called a periodic table if they're not periodic properties? And we'll get into those. And so there's about, right now, there's about 118 elements, and people are working on making more of them all the time. You may wonder why people are bothering to make these new elements. Well, physicists think that, because most of these laboratory created elements are there for only a really short amount of time. Like when you get up to element 115, 16, 17, and 18, they exist for just fractions of a second and then they're gone. So why would you bother? Well, physicists think that if we get elements big enough, like around 135 or 140 or so, they'll start to get stable again. That is a hypothesis. And so they're working on trying to figure out whether that hypothesis is true. So there's about 90 that we actually occur naturally on the Earth that we can actually dig up and find. And about 24 or so and more have been created artificially in labs. So here, man, you're going to get tired of looking at this. Hopefully everyone has a periodic table. I think I put a link to like a really good website that has a really good periodic table for you to look at. And you can click on each one of the elements and it gives you the atomic number, the symbol, the mass, gives you the density, tells you like what it's like at what are its properties at room temperature. I mean, all that kind of stuff that's in there. If I haven't, I will do that because you can use that when you're taking the test. That is all the information you're going to need. So one thing to remember that we're going to be talking about a lot later is periods and groups. Groups go up and down. So this is group 1. So everything below the 1 is group 1. And then here's group 2, and then 3, 4, 5, all the way across. And then we get into 14, 15, 16, 17, 18. And one thing that these groups have in common is that all the elements in those groups have very similar chemical properties, almost identical chemical properties. Can anyone tell me what this group is all the way over to the far right? What group is that?
Noble gases.
Noble gases.
Excellent, the noble gases. Yeah, and why are they called that?
They're completely stable.
So when you say they're completely stable, what does that mean? That term stable has a lot of different meanings.
Well, isn't it their outer shell is completely filled with electrons?
Dang, you're getting way ahead of yourself. But yes, that is true. But so if their outer shell is completely filled with electrons, what chemical properties do they have then? So you sort of touched on it when you said that they were stable. When something's chemically stable, what does that mean?
They don't degrade. I don't know.
They don't degrade. That's true. But tungsten doesn't degrade either. It's very stable. But it's different from the noble gases in one respect.
Is it that they don't give away electrons as easy?
That's true. More simply, I'm looking for sort of something more simple than that. You're right. Something simple.
Less reactive?
Yes, there you go. Yeah, much less reactive. In fact, helium, neon, and argon, the first three here, 1, 2, 3, are basically completely unreactive. We've not been able to make compounds with any of those. However, we have been able to make compounds with krypton, and xenon. So you can get them to share their electrons, but it's really, really hard. So basically, they're the most unreactive compounds on the table. Now compare that with this group, the very first group. That is probably the most reactive group on the list. In fact, so reactive, like lithium, sodium, potassium, if you were to take those and throw them into water, what do? Anyone seen that reaction? If you take a lump of sodium and you throw it into water, what happens?
Dissolves.
It doesn't just dissolve, something else happens. It explodes. Yeah, it is super reactive. And the reason for that is this group 1 over here has basically 1 electron in its outermost shell. And we'll talk about shells and all that a little bit later. That's coming up fairly soon. They have 1 electron in their outermost shell, and they can't wait to get rid of it, because once they get rid of that 1, then they achieve stability and become pretty much unreactive. And so as we go across, this group 1 has 1 electron in its outermost shell. Group 2 has, surprisingly, 2 electrons in its outermost shell. And then we'll ignore these in the middle for right now. Anyone know what these elements are in the middle? These elements right here, they're sort of right in the middle of the
metals.
They're metals, that's right. They're a particular kind.
Transition metals?
There you go. Man, people are remembering all their old high school chemistry. That's right. They're transition metals. And the reason they're called transition metals is because they give up different amounts of electrons to different other elements. So they can give up 1, 2, 3, sometimes 4, 5, and even 6. And so they're all different. Group 1 always gives up 1. Group 2 always gives up 2. And then when we come over here to 13, 14, 15, 16, 17, group 4 shares 4 electrons. Group 15 shares 5. 16, they have 6 in the outmost shell. 17, they have 7 electrons in the outermost shell, and they pick up 1. So we'll talk a lot more about this a little bit later. This is sort of just gives you a sort of a general feeling of the periodic table. And we're going to be talking about the properties and, trying to make sense of, why does the periodic table look like that? And there's a really good reason, really fascinating reason why it looks like that, but it has to do with math. But we'll talk about that. So atoms, smallest, like mentioned before, smallest particle of an element that has the properties of that element. So we can't break an element down into anything smaller than an atom. And it's not a new idea. Actually, the word atom is an old Greek word. And these two scientists of their time, Leucippus and Democritus, came up with it about 2,500 years ago. But it wasn't until the 1800s that John Dalton supported that hypothesis. That's a really old hypothesis. And basically, you would say that was a law, because no matter how many people tried to disprove it, it wasn't disproved, but no one knew what nobody knew what an atom was, but you couldn't break it down into anything less than that. And it wasn't until John Dalton came along that supported that hypothesis with quantitative measurements. So what's the difference? Someone tell me what the difference is between a quantitative measurement and a qualitative measurement.
Quantity is the number, the amount.
Not only that, yes, that's right. There's an amount, and what else? It's really important. When you measure something in science, you get a number and
Unit.
unit. Oh man, bingo. In fact, it's so important that we actually have a unit named after Dalton, and it's the unit of mass. 1 Dalton is equal to 1 atom of hydrogen. So, so we still talk about Daltons today. We don't talk about them in chemistry so much, but in biochemistry and biology, we talk about Daltons all the time. We measure molecules in Daltons, like proteins. We measure them in Daltons and kilodaltons and stuff like that. So that's an atom. So a molecule, basically, it's just 2 or more atoms, and they don't have to be different. They could be the same, connected by a chemical bond. So this is a molecule. It's just 2 atoms of hydrogen bound together, but it's also a molecule. But there's that chemical bond in between. Atoms we can actually see. We've developed technology. We can actually visualize them now. So here's like a big nugget of gold, and you can actually use a microscope to drill down and see each of these spots is an actual atom of gold. And so we're to the point, luckily gold atoms are pretty big, so we can see them. Hydrogen atoms, you really can't see them yet. They're too small. Even using a lot of different technologies, we haven't been able to see those yet. But a gold, nice and big, it's got lots of protons and neutrons in there that we can see. So big enough for us to actually detect. So molecules, there's not that many elements exist as individual atoms. There's very few. That's one of the differences between the noble gases and everybody else. Noble gases exist by themselves. So if I have a molecule of helium and an atom of helium, the same thing. It just has helium by itself. It doesn't bond to anything else. It's just helium. Hydrogen is different. Hydrogen is this, and we put a 2 down here to say that there's 2 atoms of hydrogen. Helium is just 1. Same thing with neon. Neon is just 1 atom, not bound to anybody else. But you'll notice, one of the things you'll notice when we start doing these experiments and looking at different reactions, most gases are molecules. Almost all gases are molecules except the noble gases. So you look at hydrogen, it's H2. You look at oxygen, it's O2. You look at nitrogen, it's N2. Phosphorus is another element that exists as a molecule. Usually, phosphorus is found in a lot of different formations. This is one of the more common, is 4 atoms bound together. Sulfur, when you just dig up sulfur, you get that bright yellow sulfur. It's in a state where there's 8 atoms bound together. And so later on, when we talk about moles, a mole is the amount of atoms or molecules that equals its weight in grams. So a mole of helium is 4 grams per mole because it has 2 protons, which weigh 1 each, and 2 neutrons, which weigh 1 each. So if I had a mole of helium It's the number of molecules it would take to get to 2 plus 2 is 4 grams. Now, a mole of oxygen, one oxygen atom is 16, but a mole of oxygen would be 16 plus 16 equals 32 grams in a mole. Why? Because oxygen doesn't exist by itself. It's not oxygen, it's not O, it's O2. And the reason, we'll learn the reason for that is that oxygen by itself is extremely reactive. If I have just an oxygen atom, it is going to react with something. It's extremely reactive. And if there's any more oxygen around, first thing it's going to do is interact with itself, or if there's anything else around, it's going to bind to it. Oxygen is really, really reactive. One of the reasons why we breathe it into our bodies is because it performs a trillion different chemical processes inside your body. It's extremely reactive. And we'll talk about moles a little bit later as well. So moles can also, molecules can also, as you well know, have 2 different atoms. And 2 of the more common ones, water, super, super common, 70% of the earth is covered with it, and CO2, which is kind of important chemically now. And if people are interested in global warming, that sort of thing, why CO2 is a greenhouse gas, we can discuss that later as well. So each one of these molecules has different atoms in it. Oxygen, hydrogen, carbon, oxygen. Here, carbon, oxygen, hydrogen. So I think I'll just do this one and talk about a few more questions. So differences between pure substances and mixtures. And this sort of goes back to that picture I showed you, the very first slide, where we had a fractionation tower or a cracking tower, where you took crude oil and broke it down into a whole bunch of different molecules. That is obviously a mixture because you can separate it into all sorts of different things. Now, a pure substance, you can't break that down into anything else without using some kind of chemistry. So a pure substance, like an element, you can't break down into anything else, like gold, phosphorus, oxygen. You can't break them. Those are pure compounds, pure elements. You can't break them down into anything else. Compounds you can. These are all, you can use chemical methods to break these down. Now a mixture is different. A compound you can only break down by using chemistry. A mixture, you can use non-chemical methods to break down. Like for instance, here we've got mercury oxide, this powder, sort of reddish powder is mercury 2 oxide. You heat it with a torch, and you see you can get these sort of silvery drops on the side of the tube. That's pure mercury, and oxygen gas is released from the top. And we call that a decomposition reaction, because I take something that was 2 different atoms, and I've broken it down into its constituent parts. Now, a mixture, I can separate those by physical means. Like if I have salt water, for instance, all you need to do is evaporate the water and you're left with whatever else is there. So that is a physical change because I haven't changed anything. The water's still water. That's one of the main things that like high school students have a hard time with, is when you boil water, they think that you take liquid water, that would be liquid water, and when you boil it, you change it to hydrogen gas and oxygen gas. And that's not true, right? I mean, we just changed it to water as a gas. Because if we were changing it to hydrogen and oxygen, you'd have a lot more explosions in your kitchen than if you just changed it to water. So I'm going to leave it there, and we'll pick it up tomorrow at the same time. Any questions before we go? Everyone's asleep. Oh dear, it's not a good sign.
We still have the recitation tomorrow at 12.
Yes, at noon. Mm-hmm.
Okay, thank you.
Yep. Yeah, so just either have your computer, you can print it out or just have it on your computer. Just look over it before we start. And so whatever ones you're having trouble with, we'll review first. I'm not going to review everything. We'll just review the ones that people are having trouble with. And then if you have any other questions about that or anything else, whatever time we have left, we can do that.
Do you know when Professor Grabov is going to send us Canvas invites for his lab?
I think he sent out.
He just posted it.
I think he sent out the Zoom invites for his lab already.
Zoom invite is on Canvas.
Yeah, but he should have gotten an email or something about it as well. So people in his group have not received that?
I received it.
Let me go look my email. Let me
I
check
think
my
he
email.
just sent it out like a moment or two ago.
Okay. Yeah, either send me or him email in the morning, or send right now. It doesn't really matter. If you haven't received it, and yeah, he'll send you one.
I think he just sent it out right now.
Okay.
I have a question. Are you be releasing dates on when our exam dates, just to put it on the calendar?
Yeah, I'm gonna keep that a secret. No, I will. I think the lab exams are on the calendar in the syllabus.
I saw the lab exams, but I didn't know if that goes the same for the other lab.
Oh, yes. We're going to give the lab exams to everybody at the same time. Yeah. The lecture exams, yeah, we haven't put those in yet because it'll depend on how quickly or how slowly we're getting through the material. So probably the first one will be in 3 weeks, and the second one like 2 weeks after that, and then the third one will basically be like the final. Because man, this class goes by so fast, you have no idea. Or unless you've taken the summer classes before and realize how quickly they go past. Any other questions?
I just had a general question on if we were going to cover anything like quantum mechanics.
But that's what we do. That's one of my favorite parts of the whole class is quantum mechanics. Don't be frightened. Quantum mechanics is fun. I know you think that's insane, but it's cool. Because believe me, I'm not going to be asking you to derive Schrodinger's equation. I mean, I don't understand Schrodinger's equation either. I don't think Schrodinger did personally, but yeah, what we're going to do is it's important to touch on that, because basically what quantum mechanics does is explains all of the periodic table. That's why it's such a genius advantage. It's such a huge advance to science. Was that, and I'll talk about that when we start talking about the periodic table in like chapter 2 and 3. We didn't understand how the periodic table worked until Schrodinger came along, and then all of a sudden everything fell into place. And so that's why it's so important. So like I said, I'm not going to make the math is not going to be difficult with it, because I don't understand Schrodinger's equation. So, but what I do understand is the beauty of it and how it describes everything so well. And that's what we're going to learn.
Thank you.
Yeah. Don't be scared. It'll be fun.
I have a quick question for the recitation.
Mm-hmm.
So what if we decide to show our work on a separate piece of paper? Are we able to like take a picture of it and upload that?
That's exactly what we'll do. Yeah, that's how that's how you do it. Yeah, so you
cool.
You don't have to print them out if you have trouble with that. But yeah, just write your answers down on a piece of paper, just a click. And then what is really important, because it makes it very difficult to grade, and grading's a pain at the best of times, is get it all into one file So take those pictures, like drag them into PowerPoint or something, and then, so they'll all be different slides, and just save it as one file. That would be great. Because some people just like they'll, like on their tests or something, it'll be like 12 pages, and they'll take 12 slides and they'll submit each one separately and in different order. And oh my God, it becomes really, really tough to grade. So I think the main thing would be to get it into one file, either like a Word file or a PowerPoint file, or I think the best is a Adobe file, because then once it's in Adobe, you can't mess with it.
Okay, perfect. Thank you.
If you have trouble with that, yeah, just let me know. I'll try to help you out with it.
Thank you.
Yeah.
I have a question, Professor. For the homework, it's gonna be just related to lab report. There is no other homework for
the lab reports and the recitations. Yeah, that's the two main parts of the work: the lab reports and the recitations. And I think Dr. Gagreb is giving homework as well. I haven't decided, but I haven't evaluated the different ways of doing that yet. So if you're lucky enough to have him for your lab, you may be getting extra stuff to do.
Can we switch?
No, I should throw him under the bus there. Yeah, actually, I don't know what his plans were. I think his plans are to have extra homework.
And if I study from the slide, it's gonna be enough, so I will not be, I don't need to use the book, or I have to use
I would use it. What the book is really good for is, I mean, you have enough of my blathering already, but it gives you a different way of looking at the things we talk about, and it has questions at the back of each chapter and answers for like half of them. So I think either the even or the odd questions have answers at the back. And so you can do those problems and then check on your answer to see if it's right or not. And I've been known to occasionally pilfer the text to take questions for final exams and such things. So that's why, and it doesn't cost you anything. So that's I would download it, and yeah, you use it as a resource for studying.
Okay, I have another question. For the exam, you will give us a study guide for each exam, just to follow which one I have to focus in the exam, or no?
Probably. Yeah, I mean, I just give just sort of a general outline, just like these are the top that are going to be covered. I won't go into much more than that, but I mean, because we're going to be doing problems in the recitation periods. I mean, those are the kind of problems you're going to be doing. So like by the time we do the first exam, if we've done recitations 1 through 5, and you know how to do all the problems of recitations 1 through 5, you're going to kill the exam. So I would focus on that, and the problems that we do on some of the slides will have problems on them that we'll do together, and the ones in the end of the chapters in your text. If you can do all those, you're good to go.
Okay, I know it's earlier to ask you this question, but I want to get idea how it's gonna be the exams since it's online.
Oh, I'm going to just release them on Canvas, and you'll have 24 hours to finish it and submit it back to Canvas.
So it's not like limit time and have to open camera or?
Nope. I don't like doing that. I think that I don't like putting time constraints on people. It freaks people out. I don't like doing that. So I think this allows you to go to the bathroom and drink some coffee and eat your lunch and have a nap and whatever it is you need to do.
And this will be for lab and lecture exams, so both of them
Yes.
same strategy.
Mm-hmm.
Okay.
Yep. Okay, so I will see approximately half of you tomorrow. All right, so noon. I will send out Zoom announcement in the morning. Okay, but so yeah, so download Recitation 1, have a look at it. on it a little bit, see which ones make sense to you and which ones don't. And we'll work on it together tomorrow, okay?
Quick question. Is J7 doing the same recitations?
Yes. I think both
Okay.
sections are doing the same ones. Yeah.
Okay, thank you.
All right. It's good seeing some of you and good talking to everybody. We'll see you tomorrow.
Thank you.
See you.
Thank you, Professor.